Okay, good morning to everybody again. In the lesson of today, we will change our topic. Last week, we gave some very short introduction to the theory of analytic functions of one complex variable. In this lesson, we will talk about asymptotics. And why we will do that? Well, basically because the alternative approach to the determination of, for example, electromagnetic waves, that is the numerical approach, may be in some cases very cumbersome in terms of the involved resources, say memory, CPU time, etc. And if the objects you wish to study, for example, say warship, as in this picture, are very large in terms of the wavelength, then a purely numerical approach may even not be feasible because of the very extremely large number of the unknowns which you would need to determine with a given accuracy the solution. In any case, even if the numerical approach is feasible, then usually it does not provide you much physical insight into what's happening in terms of wave processes. On the contrary, asymptotic representations, or as they call them, asymptotic expansions of these wave fields, have the opposite complementary advantages. That is, the expressions you get are quite simple. They can be understood in simple terms. You can get a high degree of accuracy by using just a small number of terms. However, this is true in the asymptotic limit, for example, when the wavelength is much smaller than the involved dimensions. And most important, from our point of view, you get physical insight into the wave phenomena that are involved in, for example, your scattering problem or radiation problem. So this is the motivation why in this lesson and also in the next one, we will try to provide some basic information on the concept of what is an asymptotic expansion. This asymptotic expansion can either be derived directly from the equations of the wave field, for example, from Maxwell equations for electromagnetics, or more generally from the wave equation or from the Helmholtz equation. And this is the example of ray optics that we will cover in the next lesson. Or asymptotic expansions can also be derived from alternative representations of the wave field, which are usually derived after writing down the equations, so the so-called Integrand representations of the wave field. And this will be the subject of the lessons that will be given in the next week. Okay, so let us start our very general and behavioral survey of what an asymptotic expansion is. And to start with, we will examine an example of a special function known as the error function that I'm sure you will be very familiar with because it's used in a number of applications ranging from probability to signal processing, etc. Okay, the definition of this special function is given in terms of this integral, in which you can see, apart from the numerical factor 2 over the square root of pi outside the integration sign, then you have an integral, generally in the complex plane, from the origin to a general complex value z, of the exponential e2 minus u squared, where u is the integration variable. Consider that the integrand function, being an exponential, is an entire function. Now we know what this means. This means that the exponential is analytic in the entire complex plane. And so it does not matter what kind of path you use to join the origin with the point z, because the value of the integral will be always the same. There are no singularities involved, so no poles, no essential singularities. So you always get the same answer, numerical answer, and this answer defines the error function. In addition to being important in many applications, this function provides a very useful starting point for discussing asymptotics, and it has also an historical value because, as we will see in a moment, it provides it provided one of the earliest examples of the so-called Stokes discontinuity, that are typical discontinuous phenomena that occurs in the asymptotic representation of functions. Okay, let's see how we can manage numerically with this error function. one approach could be the following. Since we do not know in analytical terms, and we cannot know in analytical terms, the antiderivative of the integrand, otherwise we would be able to write down the error function in analytical terms. Since we are not able to do that, one thing we can try to do is to expand the integrand as a power series, which we now know is permissible because the exponential was defined in terms of a power series which converges everywhere in the complex plane, and in particular, this series is absolutely convergent for any complex variable. And it's also uniformly convergent on any closed and bounded subset of the complex plane. Or as they say in short, the series converges uniformly on any compact set of the complex plane, where compact is a short way of saying closed and bounded. Okay, if you then insert this expansion as a power series of the exponential inside the integral sign, and you switch the integration and the summation, which is permissible because of the uniform convergence allows you to do that, then you are able to integrate term by term these simple monomials, and what you get is an infinite summation representation of the error function, which is still not a closed form representation, but at least can be calculated numerically. I mean, you can start summing up those terms one after one, and since this series is convergent for any complex value of the variable z, then you are sure that if you add up enough terms, you will be able to get an answer as accurate as you wish. Okay, the point is, how many terms do you need to add in order to get an accurate answer? So this series is theoretically exact for any magnitude and phase of the variable z. However, it is easy to see that it is numerically quite inconvenient unless your variable z is small in absolute value. Why that? Well, because if you examine closely the behavior of the terms you have to sum, then you will discover that the individual terms of this series do not begin to decrease until the index, the integer index s, is of the order of the squared absolute value of the variable z. So if z is large in absolute value, then you will need to reach at least this integer index if you wish to see that the terms in the series start decreasing, which is, of course, a necessary condition to get convergence, but is not enough, because in order to be decreasing, also you should sum enough terms in order to get a desired accuracy. So if you wish to have an at least acceptable approximation of the error function, it turns out that you need about 3 times as many terms as this value reported here. So you may need a large number of terms to get an accurate result. But what's even worse is that the error function is a very rapidly decreasing function of its argument. So for large absolute values of z, its value is a very small number. However, the series representation of the error function is given in terms of this infinite summation whose first addends are not small numbers. So basically, we are trying to obtain a numerical answer in terms of a very small number by summing numbers which are not very small. So what happens is that there is a large cancellation. For example, the first and second addend in this series are very large numbers if you compare them with the final result, but they may have quite opposite phase, so they almost cancel. Well, and then this cancellation is numerically very inconvenient, because if you have a cancellation of large numbers, then you will need to represent those large numbers with a huge number of digits of accuracy if you wish that their difference or algebraic sum remains accurate, because in the cancellation you lose lots of those digits of accuracy. Okay, so this is what the meaning of what's written here. For large values of z, the final sum is very much smaller than the largest individual terms, and so you need many extra figures, which may not be available on your computer. Okay, so there can be a loss of accuracy because of a purely numerical issue. So even though we have an exact, in principle, convergent expansion, this may be numerically useless. Let us see the opposite approach, the asymptotic one, which is an alternative approach to the calculation or the estimation of the error function. And we will see that this approach has a complementary behavior. So it's more and more accurate as the value of the absolute value of the complex variable z increases. So, for instance, let us consider first the phases, the arguments of the complex variable z, bounded by pi over 2. So we are in the right half plane of the complex plane, okay? Okay, with this limitation, we start with the well-known Gaussian integral, that is, the integral in which the upper limit, z, goes to infinity in the error function, and this particular integral, in the definite integral, can be calculated in a closed form, and the result, as you may know, is the square root of pi divided by 2. Why do we need this? Well, because now, knowing this, we can rewrite our error function by changing the integration limits, which went from 0 to z, to go from z to infinity, okay? So basically, we have added the piece from z to plus infinity, getting this Gaussian integral here, which gives you the constant 1 in this expression at the bottom. And then you remain with another integral, which goes from z to infinity. So in a sense, it is the tail of the Gaussian integral, okay? Why do we need to do this change? Well, because now the variable z is in the lower integration limit. And now if you observe the integrand, which is the exponential e to minus u squared, you will see that this integrand is a decreasing function on the real axis, at least, which attains its maximum value at the lowest integration limit, that is exactly at z, okay, at least on the real axis. So therefore, it is a good idea to expand the integration, the integrand function about this point where the integrand is most significant. So if we choose, for example, as an expansion parameter, the difference between u squared and minus z squared, and we call this new variable w, then we rewrite the integral in terms of this new variable. So this is a simple change of variables. So you end up with this expression in which you can see you can bring outside the integral this e to minus z squared exponential. Then there is also a z term in the denominator. And now the integrand has become a simple exponential e to minus w times 1 over the square root of 1 plus w over z squared. Okay? What's the use now of having changed variable? Well, now we can make use of a series representation of this latter term, that is the so-called binomial theorem, which provides you for a power series representation of the square root function. You can see here in particular, this is the development provided by the binomial theorem for this term, that is 1 plus w over z squared to minus 1/2 is equal to the power series here, in which you can see there is an index r, which goes from 0 to infinity. Then there are two factorials, r minus 1/2 factorial divided by r factorial, and then there is a power of minus w over z squared. So this is actually a power series in inverse or negative powers of the variable z. We can make a short detour on what's the meaning of a factorial for a non-integer number, because you can see in the numerator here you have r minus 1 over 2, which is a non-integer, half-integer number. So we need to extend the usual definition of a factorial, and perhaps you may know that it is possible to extend the factorial to non-integer numbers, and one way, the most common way to do that, is by introducing a special function which is known as the gamma function. This gamma function is one of the infinite possible ways to interpolate the factorial, which by itself would be defined only on integers. So if you plot the factorial, you get a set of discrete points as a graph. But then it is possible to join those points in a smooth way, and probably the smoothest way is to use the gamma function, which is defined in terms of the integral you can see here. the integration goes from 0 to infinity, there is an exponential e to minus w, and then the power w to z minus 1. This kind of integral converges as long as the real part of z is larger than 0, and this provides you an extension of the factorial z minus 1 factorial, which is by definition the gamma function, for any value of the complex variable z with real part greater than 0. Now, actually, the gamma function can be extended in the entire complex plane, with the exception of poles, which are located on the negative real axis and at the origin. You can see a plot of the absolute value of the gamma function here at the bottom right, where you can see that the poles give rise to those sort of pinnacles in the absolute value of the function. And then there is the behavior of the gamma function on the real axis, which is extremely increasing rapidly because it's the factorial, which is a very rapidly increasing function of its variable. Okay, it turns out that the gamma function is an analytic function except for those poles, and so therefore it is a meromorphic function. Okay, having said what we mean by a factorial for a general complex argument, then we come back to our series. If we insert the binomial expansion inside the integration made with respect to the variable w, what happens is that you can integrate again term by term, and the result is this one, which you can see integrated term by term. You get this blue integral, which is again, by definition, the gamma function, so it's the factorial of the index r. This factorial cancels the factorial which is here in the denominator. Okay, so in the end you get this asymptotic expansion of the error function, 1 minus e to minus z squared over z pi, and then there is an infinite summation in inverse powers of the variable z. Okay, this asymptotic expansion has been derived under the assumption that the argument of the variable z is less than pi over 2. What's the use of this alternative representation of our error function? Well, if you study the behavior of this infinite summation, you will discover that its behavior is completely different from the behavior of the power series we obtained in the initial approach. There is, in particular, in the asymptotic series, the terms first progressively decrease in magnitude, then they reach a minimum around the index r more or less equal to the absolute value squared of z, and finally they increase. Whereas in the convergent expansion we saw at the beginning, the behavior was opposite. The terms first increased and then they decreased. So because of this, this asymptotic series cannot be convergent, because as you may remember, in order for a series to be convergent, its terms must ultimately go to 0 in absolute value, whereas in this asymptotic series, the opposite happens. If you increase indefinitely the value of the index r, then those terms will increase after the minimum reached at this particular value here. So this series is divergent. Nevertheless, even if the series is divergent, so you cannot reach any numerical answer by summing all its terms, it can be of use, and it is useful in fact, because you will never sum all its terms. What you will do is that you will retain only a few number of its terms, most often only the first term, and use it as an approximation of, in this case, the error function. Okay, so the use of an asymptotic series like this one is to stop the series up to a given upper index, which could be also the first index, r equals 0, or maybe you could stop at the smallest value, at the index for which the addend has the smallest absolute value. And by doing that, you will discover that you will obtain remarkably accurate numerical results, which are even more accurate if you increase the absolute value of the variable z. Okay, this is the key of the asymptotic expansion, and this is why asymptotic expansion are ubiquitous in physics, much more than convergent expansions. And it's quite funny that it is so, because as the mathematician Giancarlo Rota wrote many years ago, usually our approach to mathematical analysis is based on the concept of convergence, of convergent expansions. So we learn many criteria for judging if, say, a series is convergent or not, whereas in practice, the most useful series we will encounter in our research, we will not be convergent, but rather they will be asymptotic. So there is the problem of teaching this to young people without scaring them. Actually, that there is something scaring in the divergence was something very clearly perceived, for example, at the beginning of the 19th century, where mathematical analysis was being formalized. For example, the mathematician Abel was very worried about the use of divergent series, which, according to him, they were the devil. So you should stay away, not even mention a divergent series. However, in, say, half a century, things had very much changed, and actually Heaviside, who, by the way, was an engineer and not a mathematician, was much more optimistic about the usefulness of a divergent series. So, as you can see here, if a series is divergent, then probably you can use it for some practical purpose, much more than if it were convergent. Okay, so this is why, basically, all this introduction to provide you a motivation why we should be interested in asymptotics, but I'm sure you have already encountered many asymptotic methods in your life. Actually, they are ubiquitous. For example, if you have found methods or studied methods such as the Wenzel-Kramers Brillouin method in quantum mechanics, or any other wave phenomena in which you can use it, or, for example, stationary point methods that we will see next week, or more generally, any kind of perturbative expansion, for example, in quantum field theory. Well, in all those cases, you will deal not with convergent series, but with asymptotic series. And so you will find asymptotic series in fields as diverse as oceanography, seismology, optics, any wave phenomena, so applied electromagnetics, quantum mechanics, and quantum field theory, of course. Just to give you a simple example in practice, so that this is true, for example, take the factorial again. It's very common to approximate the factorial by using the so-called Stirling or Stirling-Laplace asymptotic formula for the factorial. If you have studied statistical mechanics, you have made use of this formula very many times. Whereas it is completely unknown to users the existence of an asymptotic, of a not asymptotic, but of a convergent expansion of a factorial, which is in practice useless, because you would need to sum thousands of terms of this convergent expansion to get an accurate representation of the factorial, whereas the Stirling asymptotic formula is extremely accurate as long as n has a value larger than, say, 6, 7 or so, okay? Here is a nice taxonomy of the late terms of a series from which you can judge if you are dealing with an asymptotic or a convergent series. For example, typically asymptotic, that is divergent series, are of this form: a factorial divided by a power of some variable, the z variable in our examples. On the opposite side, there is the convergent expansions, in which the factorial is at the bottom, so in the denominator, and this gives you convergence. There is also an intermediate behavior, which is the so-called hypergeometric type, because you can find it in the definition of the so-called hypergeometric function, in which you are neither convergent nor divergent, but you are conditionally convergent. That is, the hypergeometric series has some finite radius of convergence. Inside this radius, you have convergence. Outside, you have divergence. And this is typical of cooperative phenomena in which there is some transition point. So, for example, ferromagnetism, in which you have the Curie temperature, or Fermi-Thomas screening. Also, boundary layers in hydrodynamics, in which you have a change of scale from what happens close to the surface and what happens far from the surface. In all those phenomena, you will find this kind of intermediate behavior, which is not so convenient, because the best one could hope is to have a divergent series in practice, because that in practice will give you the best numerical accuracy with just a few terms. Okay, to finish our introduction, I will show you on the example of the error function what a Stokes discontinuity is. So we will start over by considering again the definition of the error function, but now we will consider the argument of the variable z to be exactly equal to pi over 2. That is, instead of being less than pi over 2, we will now place ourselves exactly on the imaginary axis. So pi over 2 or minus pi over 2. So if we start with the positive imaginary axis, then we can let z equal to jy, and then we can change variable in the integration domain by letting u equal to jv. And so in terms of this new variable v, this is the definition of the error function on the positive imaginary axis of the complex plane, okay? So with this representation, we can proceed exactly in the same manner we have seen before. So we see that the integrand is large, only close to the upper integration limit, that is when v is equal to y. And therefore, we can expand the integrand about this point. We will do that by changing variables. So we introduce the new variable f, which is equal to y squared minus v squared. And so we get the integration at the bottom in terms of this new f variable, in which again you can see there is a square root, which can be expanded using the binomial theorem. Now, actually, we will need to make some intermediate step before introducing the binomial theorem. We can consider that the integration, the integrand function is real inside the integration range, because you can see when f goes from 0 to y squared, then the argument of the square root is positive, so the result is real. Whereas if you consider values of f larger than y squared, then you would get negative values here inside the square root, and therefore purely imaginary values. And for this reason, you can extend your integration to plus infinity and then take the real part, because then in this case, the result is exactly the same as if you had integrated only up to y squared, okay? The use of doing that is that now we can integrate easily from 0 to plus infinity, term by term, the binomial expansion. And in the end, we can even remove the real part operator, because if you observe this infinite summation, you will see that all the terms are real, so you don't need to enforce the real part operator. So you end up with, again, an asymptotic representation of the error function, which is now valid on the imaginary axis. You can do the same on the negative imaginary axis. So this asymptotic series here at the bottom, inside the box, is valid for any purely imaginary value of the integration variable z. Now, it's interesting that this asymptotic series is not the same asymptotic series we obtained on the right half plane of the complex plane. You can compare the two results. This is what we obtained before, when the argument of z was less than pi over 2. And you can see there are two terms, a constant one, and then this asymptotic series. Whereas on the imaginary axis, we have only the asymptotic series without the constant. Well, this is typical, the typical landmark of a Stokes discontinuity. A Stokes discontinuity is the abrupt appearance or disappearance of some term, some associated function, as they call it. In this case, it is the constant one, from the asymptotic expansion as you change the phase or the argument of your variable z across some specific values, which in this example are exactly the values pi over 2 or minus pi over 2. Which is something very peculiar, which troubled much mathematicians, because what we are trying to approximate, the error function, is not by itself discontinuous. It's an analytic function in the entire complex plane, so it's the object mathematically more distant from a discontinuity that you can imagine, because it has a C infinity function, which is representable as the sum of its Taylor series. So it's something extremely smooth. And yet, if you wish to approximate this very smooth function through an asymptotic expansion, you will never succeed in doing that in a unique way that is using only one kind of representation, but you will need different representations for different arguments of the variable z, and those different representations are different because they contain or may not contain some constant or more generally some function. So the representation, the asymptotic representation, is discontinuous, even though what we are trying to represent is not. Okay? Yes. Well, it came from the beginning. The first thing we did here, we considered the Gaussian integral, and we changed the integration domain from 0 to z, which was the original one here, in this other fashion from z to plus infinity. And this is the birth of the numerical constant 1 in our previous derivation, okay? Which was not necessary when we considered z on the imaginary axis, because I split into exactly. Okay, and what this is just an example, but this is typical.
That can be done in the axis.
On the imaginary axis, you mean? No, that cannot be done. No, if you try, you will discover that basically, because on that axis you don't have the Gaussian integral. So to have a convergent Gaussian integral, you must have a real part of z larger than 0. So you cannot do that. If you, just to finish all the possible arguments, then if you consider that the absolute value of the argument is now between pi over 2 and pi, so we are now on the left half plane of the complex plane, then there is a very simple way to get the right asymptotic formula, and it is to consider to change the sign of the integration variable u in the defining formula of the error function. So if you do that, you will discover that phi, the error function of z, is equal to minus phi of minus z. So there is a relation between what happens in the right and in the left half planes. This is technically known as a continuation formula, because if you know the behavior on one of those half planes, then you know what happens in the other one. And so you can immediately enforce this on the asymptotic expansion we obtained at the beginning, thus reaching to this asymptotic representation, which is still different, because now the constant is minus 1. So if you are on the right, the constant is plus 1. If you are on the left, it is minus 1. If you are exactly on the border, that is on the imaginary axis, the constant disappears, so you have 0. Okay, that's the Stokes discontinuity. Okay, this was just to give you the flavor of what happens in asymptotics and why, even though the involved series are divergent, they can be useful. Now we will give some basic definitions in order to adopt a terminology which is shared among us. And to do that, we will consider another example, this time even simpler, because we will consider everything on the real axis. So an integral with respect to a real variable t of a real function of the real variable t, which is the exponential e2 minus t divided by this polynomial 1 plus epsilon t, where epsilon now is a real positive quantity, which, as its name suggests, will be considered in the limit when it goes to 0. So we will consider that epsilon is a small number, and we are interested in estimating this in value I of epsilon in the limit when epsilon is a small number, in the asymptotic limit in which epsilon is small. Well, one strategy which is useful in practice to get asymptotic expansions when your function is defined in terms of an integral, one strategy you can try is to integrate by parts, because many times this provides you directly an asymptotic expansion, as in this example. Because if you integrate by parts once, then you have the finite part, which is the constant 1, minus epsilon, and then you get here another integral in which now the exponential is the same as before, but in the denominator you now have the square of 1 plus epsilon t. Okay, And you can imagine if you iterate this procedure, you will get progressively increasing powers of epsilon with a multiplier which is given by the factorial of its exponent. And then there is also a sign which alternates, -1 to the nth power. And finally, if you do that, there is n times. You have also a remainder, which is the last term here, which is expressed in terms of epsilon to n plus 1 power. Then there is an integral in which you have in the denominator 1 plus epsilon t to n plus 2. Okay? This is repeated here for convenience. And let us introduce some very common terminology. We say, for example, that this term here, minus epsilon, is of order epsilon. The next term here, 2 factorial epsilon to the second power, is of smaller order than epsilon. And we say, for example, that if you sum the first 3 terms, 1 minus epsilon plus 2 factorial epsilon to the second power, well, this is an approximation of our function I of epsilon, correct to order epsilon squared. Of course, under the assumption that epsilon is a small quantity. What do these statements mean exactly? Okay, let us define formally some symbols. For example, we have the big O symbol. These are the so-called Landau symbols. Landau was a great physicist who studied many things, among which asymptotics. We say that the function f is a big O of the function g, and we can also say that that f is of order g when k tends to k0, if there exist 2 constants, m and delta, such that your function f is bounded in absolute value by the function g, the absolute value of the function g, multiplied by the constant m, and this happens exactly inside the neighborhood of k0, which is k0 minus delta, k0 plus delta, okay? So those functions are comparable in a sense. Whereas the small o symbol tells you that f is much smaller than g, again in the same limit when k tends to k0, and you can write it also with this double sign here. This means that the ratio between f and g goes to 0 in absolute value. So f goes to 0 more rapidly than g does. And we'd also say, finally, that f is an approximation to I valid to order delta in the same limit if this happens, that if you consider the difference between I, which is what you are trying to approximate, and f, well, this difference is much smaller than delta. Okay, so the ratio here goes to 0. Now, the ordered sequence of powers 1, epsilon, epsilon squared, epsilon to the third power, etc., has this property that its jth term is much smaller than its j plus 1 term, okay? So they are progressively increasing, well, perhaps the opposite. Yes, here I should switch the j and j plus 1. So they are in increasing powers of, the increasing powers are each much smaller than the previous one. And this, by definition, is an asymptotic sequence. So an asymptotic sequence is exactly a sequence of functions which behaves in this way. The next one is much smaller than the previous one. So the representation of our function I is given in terms of an asymptotic sequence, and therefore it provides an asymptotic expansion with respect to the asymptotic sequence. Why? Well, because by definition, first of all, as we have just said, the ordered sequence of functions delta j is an asymptotic sequence if it happens that the j plus 1 term in this sequence is much smaller than the j term, okay? And then if your function I is continuous and you have been given an asymptotic sequence, then we say that the formal series, which is a linear combination of the delta j functions here, provides you for an asymptotic expansion of I if it happens that the difference between I and this linear combination is of the order of the next term, so m plus 1 term, for m which goes from 1 to capital N. Okay, so for example, if you consider just the first term, a1 times delta 1, then this should provide you an approximation of your function up to the order of delta 2. So the next neglected term. And this must be true for any index. If this happens for any index from 0 to infinity, then you are able to write this, as you can see here at the bottom, as an asymptotic expansion where j goes from 1 to infinity. And formally, you will employ this tilde, which means asymptotic equality. So when you see this tilde, you should be warned that the series, or the finite summation, but in general, the series you see at the right-hand side generally is not a convergent series, but it's only an asymptotic series. In most cases, it will be divergent. Okay? Well, maybe this is a good time to make a short break, so we will do our usual 10 minutes break. Okay? Let's have some coffee. See you later then. Okay, we can start over again. Okay, so we have seen what an asymptotic sequence is and what an asymptotic expansion is. Okay, if we come back to our example, by integrating by parts and iterating, what we get is ultimately this kind of series in which you can see there is epsilon to the jth power, then there is the factorial of j, and then there is -1 to the jth power. This is an asymptotic expansion in the limit when epsilon tends to 0, because it satisfies the definition of an asymptotic expansion. So we have an asymptotic sequence here, and the difference between the function on the left-hand side and any truncated version of the infinite summation on the right-hand side is of the order of the first neglected term, okay? However, this asymptotic series is not convergent, and actually it is very simple to see that this series is divergent, because if you fix now a given value of epsilon and you try to sum for j that goes from 0 to infinity, then because of this factorial here, this series is clearly not convergent, okay? In the absolute value of its general term goes to infinity as j goes to infinity. However, we will never use again this series by summing it. However, instead we will truncate it, for example, to the first few terms, and this will provide us for an accurate approximation of our function I of epsilon in the limit when epsilon is a small quantity. A related example, something very similar. Now the integrand is the exponential e to minus kt, and in the denominator we have 1 plus t. Now in this case, we consider the opposite limit when k goes to infinity. So it's an asymptotic limit at infinity. This function j can be reduced to our previous example just by simple change of variables. So if we introduce the new variable t prime, which is equal to k times t, and we introduce the new parameter epsilon, which is the reciprocal of the parameter k, we get that j is equal to epsilon times the integral that we considered before. Now epsilon goes to 0, of course. This is the new asymptotic limit. And if you perform exactly the same steps, you will discover that your function j can be represented in terms of this asymptotic sequence, 1 over k, 1 over k squared, and so on, plus a remainder. And this remainder can be estimated in a very simple way. You can try by yourself. You will discover that the absolute value of the remainder is much smaller than the last considered term 1 over k to n. So this, by definition, is therefore an asymptotic expansion. And we can use the symbol tilde to say that our function j is asymptotically represented in terms of this series, which is a series of inverse powers of the large parameter k. Another example, still another example, in this case, the large parameter k is not inside the integrand, but it's the lower integration limit k, okay? Again, we can integrate by parts, which is a powerful technique many times, as in these examples. And what you get if you do that n times is that you get this quantity inside the square brackets, which is a sum of terms 1 over k, 1 over k squared, and so on. This is multiplied by the exponential e to minus k, and then there is again a remainder, which can be written in this integral form, and again it can be estimated, discovering that it is much smaller than the last considered term in this expansion, so the exponential e to minus k divided by k to the nth power. So again, this is an asymptotic expansion, and we can write that I of k is asymptotic to the exponential e to minus k times this infinite summation, which again is a divergent summation, as you can see immediately if you consider k fixed for a moment and you examine the behavior of these terms as the index j increases, okay? Now, as we already said, these asymptotic series often give remarkably good approximations. For example, in this last example, when you consider, for example, the large parameter k equal to 10, and you consider just two terms of the asymptotic series, so you need only two of those terms to obtain a result for which the remainder is less than 2 times 10 to the minus 13th power, which is a very small quantity, one could say, but one should ask himself, it is small with respect to what? I should know what's the exact value of the function I wish to represent. And if you consider the exact value of the function I evaluated for the value k equal to 10, then this exact value is of the order of 10 to minus 6. So you can see that your asymptotic series truncated to the second term gives you an answer which is accurate of the order of 10 to minus 13 in comparison to 10 to minus 6. So we have a 7 order of accuracy, 7 digits of accuracy in our answer, okay, with just two terms. But even if the large parameter k is, after all, not so large, so for example, if you consider k equal to 3, which is not a large number, you would not, we would not say that this is a large number, still, in this case, of course, things go worse. But they are not so much worse. For example, the remainder is of the order of 10 to minus 3, whereas the exact answer is of the order of 10 to minus 2. So you still get some 10% accuracy with just two terms, even for a parameter k, which should be in principle large, but it is not so large in practice. In practical terms, if you have an asymptotic expansion of the electromagnetic field, which is accurate when the wavelength is much smaller than the involved objects, than the dimensions of the involved objects, it may turn out many times that your asymptotic representation remains quite accurate, even if the wavelength is not so much smaller than the involved dimensions. So for example, if you consider scattering of a plane wave by this disk, which is of the order of a meter, linear meter, then of course, if your wavelength is of the order of a millimeter, you would expect an asymptotic expansion to be very accurate. But it turns out that even if your wavelength is of the order of 30 centimeters, say, okay, it may happen that your asymptotic expansion gives you still some accurate, maybe not extremely accurate, but still an accurate result, which can be a starting point, at least, for your design, okay? Once you have an asymptotic series, we have said that the behavior of its terms is that they first start decreasing in absolute value and then they ultimately increase. So one optimal choice of the truncation index would be that of choosing the index for which the term in the asymptotic series has reached its minimum, because at that point you would expect the highest accuracy. This is sometimes done. This is not very common, because you should estimate where the minimum is. So in the most common situation, you just consider one or two terms in your asymptotic series. When possible, you could also optimize, so truncate at the least term in absolute value, and this is sometimes called the super asymptotics, because this gives you the best possible accuracy for a truncated series. It's not always the same, so you should study case by case where the minimum is. There is also the possibility of doing better than super asymptotic, and this is the subject of hyperasymptotics, we will see in a moment. Let us state some properties of asymptotic representations or expansions. For example, given an asymptotic sequence, delta j, of a large parameter k, then the asymptotic expansion of a function f of k is unique with respect to that asymptotic sequence. In fact, if by contradiction you assume that there are two different asymptotic expansions, one with coefficients a and the other with coefficients b, then if you define the coefficient c as the difference between a and b for any index j, of course, then you would find of course, that 0 would be asymptotic to this asymptotic sequence involving the c coefficients. But now dividing, for example, by delta 1 and taking the asymptotic limit, you would discover that c1 is equal to 0. And then you can repeat. You can divide by delta 2 and discover that c2 is equal to 0. And in this way, you will discover that all those c coefficients are equal to 0. Therefore, you cannot have that A is different from B for any index J. So basically you have uniqueness of the representation. Well, this can be, of course, extended to complex parameters. Our initial example of the error function was made in the complex plane. So instead of considering a large real parameter k, you can consider a z complex variable whose absolute value is large. So our asymptotic limit is that we are studying the behavior of a function of a complex variable at infinity, the point at infinity in the complex plane, whose neighborhood is the outside of some circle where the absolute value of z is equal to, say, capital R. Well, it may happen that your function is analytic everywhere in a neighborhood of infinity, and in this case, we know that it is equal to the sum of its Taylor series in inverse powers of z. So you can represent your function exactly by a convergent power series expansion like this. And in this case, this convergent power series expansion is also an asymptotic expansion. So in the lucky case in which your function is analytic at infinity, then you immediately have from its Taylor series its asymptotic representation in terms of the asymptotic sequence 1 over z to j. However, if the function is not analytic at infinity, like the error function, which has an essential singularity at infinity, well, in that case, it can be shown that such a function cannot possess an asymptotic expansion valid for all values of the argument of the complex variable z. And this is why Stokes discontinuity must happen in this case. So typically, an asymptotic expansion is valid inside only some bounded sector of arguments in the complex plane. That is why, for example, if you take the Abramowitz and Stegun handbook of mathematical functions or any other more modern version like the National Institute of Standards collection of mathematical functions that you can find online, then in any statement of an asymptotic representation, you will also find clearly exposed what are the limits of that asymptotic representation in terms of the argument of your complex variable z. Because many times, as I said, it is impossible to find a representation that is valid for all values of the argument. Remaining within the complex plane, we say that a function has an asymptotic power series in a given sector of the complex plane, and we write that our function f of z is asymptotic with a tilde symbol to this asymptotic series, which is generally, however, not convergent. Now, if another function g has its own asymptotic power series representation with coefficients b, then it turns out that, for example, the arithmetic combinations as the sum and the product of those f and g functions, they also have asymptotic power series representations that are obtained by respectively adding or multiplying those two series terms-wise. So it's easy to perform asymptotics of sums or products of functions which have already been characterized asymptotically. Even more, if you have an asymptotic power series, you can integrate or differentiate it term by term. And what you get is an asymptotic representation of, for example, the derivative f prime or of the antiderivative. For example, here you can see the antiderivative of f minus a0 minus a1 over zeta. And integrating term by term, you get this asymptotic expansion. More generally, if you have an asymptotic series, which is not necessarily an asymptotic power series, then you can integrate term by term, but in general, you cannot differentiate term by term. This is possible if you have an asymptotic power series, which is a lucky circumstance, of course. Now, note that having given the definition of an asymptotic expansion, this asymptotic expansion can represent two entirely different functions. So if you are given the function and the asymptotic sequence, then the asymptotic expansion is unique. But if you are given the asymptotic expansion with respect to a given asymptotic sequence, then the function it represents may not be unique. And this is very simple to see. Because, for example, if you consider a function f with a given asymptotic expansion in some sector, of the complex plane, for example, when the argument of z is between minus pi over 2, here the minus is probably invisible, minus pi over 2 and plus pi over 2. And then if you add to this function an exponential e2 minus z, where again the minus is missing, okay, then it's easy to see that in the same sector of the complex plane, this new function has exactly the same asymptotic expansion as the original function f. This is because the exponential e2 minus z converges to 0 on the right half plane of the complex plane, and it does so more rapidly than any inverse power. So basically, the exponential wins over any power of z, as you of course know, and therefore we say that this exponential e2 minus z is transcendentally small with respect to all the terms in the asymptotic sequence. Or, as they also say, it's a term beyond all orders with respect to that asymptotic power series. So in this way, in this situation, it's clear that an asymptotic power series cannot contain any information about this exponential. So you will never know if your function contains an additive exponential like that or not, or better, the same asymptotic expansion is equally well suited for representing the function f, as well as any function obtained by f adding this asymptotically transcendentally small term. Okay, this is maybe considered a drawback, actually, of our definition of an asymptotic expansion. Our definition was the original one, which was given by Poincaré in 1886, so at the beyond the end of the 19th century, which was very important for historical reason because it was the first clear foundation of the discipline of asymptotics. But I would like to warn you that there are also extensions of this definition. We cannot go into this, but for example, Robert Dingle, who was a British physicist, provided in this beautiful book, Asymptotic Expansions, Their Derivation and Interpretation, a generalized theory of asymptotic expansions, which is aimed at addressing this drawback. So he wanted to have a unique association between an asymptotic expansion and a function. And he managed to do that. He discovered that actually an asymptotic series is a way of encoding precisely all information about the function you are representing, provided you use the correct definition. And actually, this issue of the exponentially small terms can be very important in physics, because typically it's associated with some physics which is not described by perturbative expansions. The most common, the most famous probably example is superconductivity, which could not be discovered by very smart people like Feynman, for example, because they were trying to do perturbative expansions. Whereas the phenomenon is by itself non-perturbative, so you cannot discover it if you go that way. You should go another way. Well, about this, you can find some very interesting details in this beautiful review by Boyd, The Devil's Invention, again the devil, asymptotic, superasymptotic, and hyperasymptotic series. And also there are a plethora of references on these. For example, I've singled out this one by Burghignoli, An Introduction to Resurgence, which is a theory related to these hyperasymptotics, trans-series, and alien calculus. The names are very evocative. Okay, let us finish by saying something again about the discontinuities. We have seen the Stokes discontinuities. In particular, here we state the same. When a function has an asymptotic representation in a sector of the complex plane, it can happen that an entirely different representation is valid in an adjacent sector. Very simple examples can be given of this. Take, for example, the hyperbolic sine of 1 over z, and consider the behavior of this function in the asymptotic limit when z goes to 0. So we are in a neighborhood of the origin, which, by the way, is a singularity of this function. It is a pole of 1 over z, but since this is the argument of the hyperbolic sine, and as you know, the hyperbolic sine is defined in terms of exponentials, then basically we have that the kind of this singularity is the same kind as the singularity of the exponential at infinity. Now, the exponential has the worst kind of singularity at infinity, the essential singularity, which is the kind of singularity for which you have an erratic behavior of your function in any neighborhood of the singularity. And the same happens in this example here. In this particular example, if you approach the origin from the right, so from the Sine part, this right half plane, then it's easy to see that the hyperbolic sign is dominated by this exponential here, the exponential of 1 over z, whereas in the yellow half plane on the left, it's dominated by this other exponential, e to minus 1 over z. So you can see here you have a Stokes discontinuity again along the imaginary axis, which separates the two different representations. Okay, so you don't have a single asymptotic expansion, but you need at least two. And this is what these are the possibilities actually that you can find in practice. If your function, as we said, is analytic at infinity, then you can represent the function as the sum of its Taylor series, and this series is a convergent one. So in this case, you have for free also the asymptotic expansion of your function, which is provided by the Taylor series itself. For example, if you have this meromorphic function, 1 divided by z plus 1, this is meromorphic because it has a single singularity at z equal to minus 1, which is the 0 of the denominator, where it has a single pole. At infinity, this function goes to 0, so therefore it is regular, and it can be expanded as a sum of this Taylor series in powers of 1 over z. This series converges everywhere outside the circle where the absolute value of z is equal to 1. And this is because on that circle we have our singularity, which is the pole at minus 1. Okay, so we cannot expect this kind of expansion to hold everywhere in the complex plane, but that's not a problem if we are interested in obtaining asymptotics in the large z limit, because z will be large in absolute value, so we don't need to cover all the plane, but only a neighborhood of infinity. In this case, this is the only case in which you have a unique power series representation as an asymptotic expansion. Whereas if your function at infinity, for example, has a branch point, like in the case of a square root function, in this example here, then if you have a branch point, as we saw in our first lesson, in order to get a single value for our function, we need to cut the plane along a rather arbitrary line that joins the branch points. In this case, for the square root function, we need to join the origin, which is a branch point, with the point at infinity, which is another branch point. We can do that, for example, along the negative real axis. But if we do that, then we have a discontinuity by definition across the branch cut, and also the asymptotic expansion will be therefore discontinuous across the cut. And finally, we have the example of the hyperbolic sign, in this case at infinity. So we have z as an argument, in which the function has an essential singularity. And this is the case which was originally considered by Stokes, and in which he found with much surprise that he needed to enforce a discontinuity in the asymptotic representation if we wish to maintain accuracy in the representation of the function, which again is a continuous function because the hyperbolic sign is analytic everywhere in the complex plane. However, you cannot represent it asymptotically by means of only one asymptotic series. You need two. One for the right half plane and another one for the left half plane. The imaginary axis being the place where the discontinuity occurs, the Stokes discontinuity occurs. Okay, I think that for today I've said everything I wished to say. What I've written in these slides is more or less contained in Ablowitz and Focus, this book about complex variables, which is more practical than the references I gave you in the previous lessons, and in which there is also a nice chapter about asymptotic expansions. And then there is this alternative approach, the one put forth by Dingle, in this 1973 book, which is rather advanced. It's not an easy reading, but it's worth knowing that something different from the standard asymptotics as the one given in Ablowitz and Focus exists. Okay, that's all for today. And again, thank you for your attention. If you have questions, you can post them here or whenever you wish by email. Okay. Thank you also to Tonino and Annika beyond the ocean. And see you on Thursday. I hope to be here in presence, but I will let you know otherwise. Okay. If you don't hear from me, I will be here. Okay.